Hello, Jim. Are you there?
Hey, Scott.
Hey, good.
All good.
Excellent. I'm glad it's working.
Yeah, no, it's fine.
Okay.
I meant to come out tonight, but they're saying foggy and slippery road. So I thought, what the heck?
No, exactly.
But
Okay, well, we'll get started in just a couple of minutes here.
Okay.
Just a couple quick announcements. Sylvia has t-shirts, Sprucewood Star Party t-shirts that are available. Just come and see her. And also there are some magazine giveaways up at the front here if you just want to help yourselves. So our first speaker tonight is for our beginner session is Gail Wise. And she's going to talk to us about Pegasus, the winged horse, and what kinds of catastrophes they may come along with that.
Wait a minute. Okay, Mike.
It's all. Yeah, it should be good. And you can just, I guess, just page down or whatever. Page down or just click that and go.
All righty. The huge constellation Pegasus the Winged Horse is one of the most impressive features of the sky. The most easily recognized part of this constellation is the so-called Great Square of Pegasus. This asterism is fairly obvious because there are hardly any other bright stars near it. This almost perfect square of 4 stars stands high between summer and winter constellations. The star at the northeast corner actually belongs to Andromeda so that she can have a head. Pegasus is a partly finished constellation. It shows only the front half of the horse and it completely ignores his wings. Pegasus is famous for being the only upside down flying front half of a horse in the entire galaxy. The stars in Pegasus have been seen as a horse since very ancient times. Now we must remember that in the southern hemisphere, he is right side up, so it is possible to see a resemblance. I like to say that he's flying loop-de-loops. A winged horse is depicted on artifacts from a number of ancient civilizations like Mesopotamia and on coins from ancient Greek and Roman cities. Pegasus appears on Corinthian coins as early as 550 BC. The myth about Pegasus begins with his unusual birth. His mother was the beautiful Medusa. She was seduced by Poseidon, the Greek god of water and horses, after which she was turned into a hideous monster with serpents covering her head. After the hero Perseus killed her, he was carrying her severed head, and some of the blood dripped into the sea. Out of sadness, Poseidon took some of this blood and mixed it with the white foam of the waves and the white sand of the beach. From this mixture sprang the winged horse Pegasus. Pegasus was a playful and kind beast. He was always seen as a light-hearted creature, a messenger between Earth and Mount Olympus. He loved to frolic around, sometimes in the heavenly fields, sometimes on the earthly plains, sometimes skimming over the waters from which he had been born. Shortly after his birth, he flew up to Mount Helicon. As one of his hooves struck the ground, it opened up a spring of gushing water. This spring became known as the Hippocrene, which in Greek means the horse's fountain. It was said that drinking this water gave the gift of poetry. Ever since, the flying horse has been seen as a symbol of poetry and the creative arts. He is also a sign of immortality and is believed to be one of the lost zodiac signs. It was the Corinthian hero Bellerophon who claimed the flying horse as his steed. Now, if you think you recognize the name Bellerophon, it was because it was the spaceship from the movie Forbidden Planet. With the help of Athena, who gave him a golden bridle, Bellerophon captured Pegasus, and he was the first to ride him. He attempted to ride up to join the gods on the top of Mount Olympus, but Zeus was not amused. Only gods and goddesses are allowed on Mount Olympus. So Zeus sent an insect to sting Pegasus, who reared up and threw Bellerophon off. Poor Bellerophon landed in a thorn bush in a distant country, and he wandered around as an unknown beggar until he died. Pegasus did fly up to Mount Olympus, and for a while Zeus used the horse to carry his thunderbolts. As a reward for faithful service, Zeus placed Pegasus among the stars, thus giving him immortality. Pegasus has no really bright stars, but he's still easy to find because of the square. He is the 7th brightest constellation, and he has 100 stars brighter than 6 magnitude. Most of the stars are magnitudes 3 and 4. And the 4 stars of the square are between 100 and 150 light years away. The brightest star in Pegasus is Markab, from the Arabic word for the shoulder. Skayat is from the Arabic for the front leg. Algenib is for the side. And this star, when it did belong to Pegasus, is Sura, from the Arabic for the belly button. And I did not make that up. And Enif is his nose. 4 degrees northwest of his nose is the beautiful globular cluster M15. This is probably the densest of the globular clusters in the Milky Way. It was discovered by Jean-Dominique Maraldi on September 7, 1746, and it was rediscovered by our friend Charles Messier in 1764. M15 is generally considered to be one of the finest objects of its kind in the northern sky. I used to be able to see it easily from my backyard until my neighbor put up a ridiculously bright light. Its magnitude is 6.5, which makes it the 12th brightest of the known globulars, just in case you were keeping track. It measures 12 arc minutes across. In binoculars, you can find it as a small fuzzy object. It has a total apparent width of 12 arc minutes, so it's just under half the size of the full moon. M15 is one of the richest and most compact globular clusters. It's 34,000 light years away from us, and it has a luminosity about 200,000 times the luminosity of our sun. And it contains a planetary nebula. Up here, that little guy right there. But that planetary is way too faint to be seen with our telescopes. The Upsilon Pegasids, have you ever heard of them? It's a meteor shower that's active from July 25th to August 19th. It peaks on August 8th with an hourly rate of 1. There are several nice double stars in Pegasus that are worth a look. 3 Pegasi is just 1 degree south-southwest of M15, so it's easy to find, but you will need binoculars in order to split it. Kappa Pegasi, this is a very close double star with a faint companion. It's a yellow-white star and an orange star. But since they're so close together, about 100 light years from each other physically, we see them as one star, even in very large telescopes. Kappa was discovered to be a binary star by S.W. Burnham in 1880, using the 36-inch reflector on Mount Hamilton. It took all of the telescope's power and very steady seeing to split the 2 stars. Well, since most of us do not have 36-inch reflectors, I guess I'll just have to take his word for it. However, there are several other double stars that are not such demanding targets. Zeta Pegasi, also known as Homan, from the Greek phrase, the Arabic phrase, the lucky star of the ostriches. It's magnitude 3.4, and it has a faint companion, which is magnitude 11. And for some reason, the Chinese associated this star with thunder. More or less marking the top of Pegasus' foreleg is Mu, which is magnitude 3.5. And together with Lambda, it was the good luck of the excellent one. In Persia, they were the good luck of the camel striving to get to pasture. There were a lot of names signifying good luck that were given to morning stars of the early spring. There is a little open cluster of 12 stars. It's NGC 7772. They're all 11th to 14th magnitude, and the cluster's total magnitude is 10. The size of the cluster is 5 arc minutes, and there's a group of 6 stars that form an almost perfect V. You can see them right there. Some observations suggest that these stars appear to be 3 or 4 billion years old. Imagine that. In 1995, the star 51 Pegasi was found to have a planet orbiting it. This planet is the size of Jupiter. This was the very first extrasolar planet ever to be discovered. The star was found to have a wobble, which would be caused by the planet's gravitational pull. The planet's orbit is surprisingly close to the star. It's only 7 million kilometers, or a little bit more than 1/20th the distance between the Earth and the Sun. The planet's surface temperature was calculated to be about 1,300 degrees Celsius, and it's covered by oceans of liquid aluminum surrounded by an atmosphere of hot vapor. This is not the place where I would like to spend my next summer vacation. As we look towards Pegasus, we're looking out of the flat disk of the Milky Way. So Pegasus is home to many, many deep sky objects. Most of them are galaxies. About 4 degrees northwest of Eta, is a tilted spiral galaxy with fine, delicate arms. NGC 7331 is almost 50 million light years away, and it's moving away from us at a rate of 656 miles per second. Its magnitude is 9.5. It's the brightest galaxy in Pegasus. It measures 10 by 2.5 arc minutes, and it's very similar in size and form to the Andromeda galaxy. Its photograph used to be used to illustrate what the Milky Way would look like from the outside before we knew that the Milky Way does not look like this. NGC 7331 is one of the brightest galaxies, but for some reason it was not included in Messier's catalog. There are quite a few other galaxies within range of our telescopes. In fact, the square is just full of galaxies. So if you are so inclined, you can spend the whole night looking within just the same few degrees. NGC 7814 is a spiral. It's seen edge on. It's about 40 million light years away from us, and it measures 5 by 2.5 arc minutes. And it's fairly bright at magnitude 10.5. Sometimes it's called the Little Sombrero because it looks so much like M104, the Sombrero Galaxy in Virgo. NGC 7741 is a typical barred spiral, which means that it has a bar-like nucleus and fairly large-scale spiral arms. It measures 3 by 2.5 arc minutes, and its magnitude is 12, so it's kind of big, but not very bright. It's receding from us at a rate of 1.7 million miles per hour. And given its apparent dimensions, NGC 7741 is about 50,000 light years across. It was discovered by William Herschel on September 10th, 1784. NGC 7217 is a face-on spiral. This is almost perfectly round, so it actually looks more like an elliptical galaxy. The diameter is 4 arc minutes, and its magnitude is 11.3. This one is also about 50 million light years away. This galaxy has a number of stars rotating in the opposite direction around the galaxy center to most of the other stars, and it has 2 distinct stellar populations. It has been suggested that these features were caused by a merger with another galaxy, and in fact, computer simulations show that 7217 could have been a large lenticular galaxy that merged with 1 or 2 smaller galaxies, becoming this huge spiral that we see today. Anyway, right now, this galaxy is isolated in space with nothing else very nearby. NGC 7479 is an S-shaped barred spiral. It's fairly large for a galaxy. It's 4 by 3.5 arc minutes, but it's not very bright. It's only magnitude 11. It's very easy to find, though, if you imagine a triangle with these 2 stars. You just kind of complete the triangle, and there it is. And this was discovered by William Herschel in 1784. It's half a degree to the south-southwest of NGC 7331 is a tight little group of remote galaxies that are called Stephan's Quintet. Their numbers are NGC 7317, 7318A and B, 7319, and 7320. If you think you recognize these galaxies, it's because you've seen them at the beginning of the movie, It's a Wonderful Life. These 5 galaxies are all bound together gravitationally, and 4 of them appear to be interacting with each other. This is the best known case of an apparent cluster of galaxies in which measurements showed widely different redshifts. The largest member of the quintet, NGC 7320, is not actually a physical member of the group, it's just in our line of sight. 3 of the galaxies are barred spirals, 2 of which are intertwined and gravitationally connected. The largest is an irregular spiral, and the smallest is an elliptical galaxy. You should certainly learn to recognize the Great Square of Pegasus. It is a valuable guide to the night sky. It measures 1 hour of right ascension from east to west and 15 degrees high north to south. The 2 stars on the eastern side are directly north of the spring equinox. This great square is high overhead from October to December. The Greeks saw it as the gateway to paradise for souls escaping reincarnation. The square is an excellent reference to finding many of the other constellations, and it is a valuable guide to the night sky. The end.
my little thing here.
Yep. So we're running ahead of time a little bit, which is fine, and we'll just carry on. So for tonight's meeting, the agenda is going to be, we just had Gail Wise talk to us about the beginner session. We'll do our meeting welcome, which I'm going to go through here in a moment. Announcements, list of membership volunteer opportunities. Brian Stock will be doing our what's up. He'll also do a report on the nominating committee for our AGM, which is next month on the 13th. What's new? Dr. Danielle Baud. We'll have a break, and then our main presentation will be Jay Anderson. So announcements, again, as I mentioned, the AGM with elections, budget, and other motions as required will be on the 13th of January, 2023. The official announcement to all the membership went out last night, so everyone should have received this announcement on the groups.io is our primary way of communicating with all the members. We are looking for volunteers for meeting presenters. So as you saw tonight, Gail was one of our presenters, and we have lots of other opportunities. If you have an interest or something you'd like to do, please let us know and we will arrange for it. Our Loaner Scope coordinator is Mike Caracas. And again, you can reach Mike through groups.io. Binocular Interest Group is Darren Henning. And on groups.io, he has his own portion there. If you want to link up to that, you can ask to join the group, and Darren will be more than welcome, more than open to having you there and filling you in all about the life and times of observing the night sky with binoculars. Just a reminder about First Fridays at the Manitoba Museum. Scott, who is up front here, is the person you'd want to talk to, and we're always looking for volunteers for that. That's just another good example of us working with like-minded organizations, and it's a great way for us to bring the science of astronomy to the general public. There is still opportunity if you wish to nominate someone for council or an appointment to one of the various volunteer positions. Brian Stack will be talking shortly, is one of the other people that will be available that's coordinating all that, as well as the nominating committee. The weather for tomorrow, didn't have a chance to look. Anybody have any idea what the weather for tomorrow is? Looks like a thumbs down. warm and cloudy. So in all likelihood, there won't be a members' night tomorrow because we're just going to be able to see clouds. Just so everyone's aware, council is working on incorporation. In particular, we expect to finalize incorporation in January. Glenlee repairs are moving along slowly, but it's moving forward. The policy and procedures manual as well. And the Nature Conservancy of Canada, we are still moving forward with the dark sky preserve there. We more or less, it's moving forward, but we've got to redo all our measurements in that. Nature Conservancy of Canada is very keen on having their designation move forward. Once we resubmit the numbers to them, it should go fairly quickly. So we're quite happy to be moving forward on that. If you want to know more about it, come see me at the break and I'll fill you in. We have calendars for sale tonight, $18 each. Abdul, hold up your hand there so everybody knows if you want to buy a calendar. Abdul's sitting there by the camera up here, and he's going to hold up there we go. Calendars are available. And for anybody on our online audience, please notify us through whatever way you want, whether it's on Facebook or that, if you're interested in a calendar, and we can make arrangements to get it to you. Oak Hammock Marsh is again going to happen this month. It's the third Thursday. Is that correct? Third Thursday? Yeah, third Thursday. All the members you can go and volunteer there. The criteria, so you don't have to pay when you go, is that you have to bring a scope so that when they set up on the roof, we're able to share with the public that comes there after the presentation that's done. So if you've never been there, it's not a bad sky for just being north of the city. Certainly the northeast and west views are quite nice. So obviously when you look south, not quite so great, but the rest of it is very, very nice. RASC store, I doubt it'll open. I'm going to try. I doubt it though. If you didn't know, the link's there. We do have a store that carries product for the RASC, and it does help support the RAC. Some members have gotten the mug, t-shirts and things like that. So if you're interested, please be aware that that is available. And also just to put another pitch in for Sylvia over there with her t-shirts, holding them up. Dark Sky Preserve t-shirts from Spruce Woods, $35. So now comes the harder part. Yeah. How do I get out of there?
Just a note that RASC Winnipeg that supports national.
RASC Winnipeg, absolutely. Oh, I got lucky. So the volunteer opportunities that we're still recruiting for, that we don't have volunteers for, a meeting coordinator. And again, the meeting coordinator is somebody who simply just arranges and makes sure we have enough speakers for all the different parts of the meeting. A volunteer coordinator is just that when we get requests from the public through the website or Facebook for support, they would work together through our groups.io website, put out a call for volunteers and coordinate those and try to put people together. Explore the Universe coordinator is basically it's what it is if, go ahead, Stan.
I've been volunteering for that one.
Oh, okay. The volunteer coordinator?
Explore the Universe coordinator.
Explore the Universe coordinator, that's the one you want? Perfect. There you go. Just so everybody knows what that is. If you weren't aware of the RASC has a Explore the Universe certificate and several observing certificates that you can work through. And the center coordinator is the person who will receive your complete for the Explore the Universe certificate. They will review your logbook and your recordings of everything you've done. And if everything's met, they will notify National, and then you'll be successfully awarded your certificate. As well, they coordinate with National for all the other observing certificates that are available. Some people, just so you know, it's not a hard certificate to complete, but the vast majority of us are still working through that certificate, to be very honest with you. But there are several. In fact, those in the room, who's completed that certificate? I know there's several in the room. So we got Gail. Gail, only one here? There you go. How many of us are working on our certificate? Oh, look at that. There you go. Mentor coordinator, meeting presenters I've already talked about. Finance committee is 3 members. Observatory committee, we can always use more help with the observatory committee. And some of the roles there are to train other new members on the dome, how to use the telescope that's there, as well as the general facilities, you know, what the protocols are. For instance, training people to sign the book so we know how many people are actually using the observatory. That data is becoming more and more important as we find if you do go out, please sign the book that's there so we know you're there, because as we look at different funding areas, people want to know how many people use this. And without being able to show them, you know, there's 300 people use this throughout the year. It's difficult to back it up. It just gives us the data. Light Abatement Committee, that's a group that would work towards educating people on dark skies and why it's important to have them. In particular, in the city, working with the city, possibly, you know, before they bring in new LEDs, explain to them that maybe these aren't the best lighting, or at the very least, that they could use a cooler color palette for those LEDs to decrease the effect it has on the night sky. Yes.
Do we have a committee right now?
We don't. Yeah, our person moved away that was running that group. So we are looking for volunteers for that committee. And of course, the awards committee as well. And the awards committee are simply look at the membership to identify people who are deserving for recognition, either on the local center awards or the national awards. And we have several people in the center who've received awards over the years. Our most recent recognition was Jennifer West, who had an asteroid named after her for her work as an astronomer. Jennifer West is a member of the center. So She may not be living here, but she maintains her membership with the Winnipeg Centre. So those are the sort of things that happen with the awards committee. Any question on any of those? Brian, do you want to come down and do your nominating? Ed, do you have to switch his on? Yeah, you can put the mask up.
I just put your presentation up.
And if you want, you can go right into.
What's up?
Yeah.
Okay, yeah. There you go. Pointers there. Just go ahead. Okay, so I advance it this way. Either way, like you can use that too as well. That or I think page now.
Scarf up here. Okay, I'll just touch briefly about the nominee committee. We are looking for people to fill in positions for the counselors. We do have some. Do you have a question? No? Okay. All right. So yeah, I'll be looking for people. We're sending another notice out for positions to fill out. And also too, we have other positions to fill out too, like the Win-Centric, something like Dennis has mentioned earlier about the Observatory Committee, the Awards Committee, the Nominee Committee. There's other positions opening. I can't recall offhand, but yes. So we'll put a notice out, and of course, at the AG meeting, again, we'll take nominations on the floor. So let's jump right into what's up for December 2022, and let's see if I can get this right this time. Okay, we'll start off with the planets, and I wish I had that remote. Makes it a lot easier for me. Okay, so simply put, we have Mercury and Venus are pretty much going to be in the evening planets. Mars has reached its opposition, December the 8th already. We're at the closest point, but it's not the biggest Mars we have yet. But I'll explain more about it too. Jupiter, Saturn, again, they're going to dominate mostly of the evening. The planets for viewing, but Mars will dominate pretty much all the skies. Now, this might seem a lot, but I'll sum it up really briefly. It's nothing more than all the major planets that we have in the solar system is going to be passing the moon. We do have two meteor showers, a Gemini and the Ursa's meteor shower. The Gemini is supposed to be the biggest one, which when I look at the calendar, it's supposed to be 150 per hour, whereas the other one is only 20, but unfortunately we're competing with the full moon. One nice thing about it is we have Mercury and Venus on the 29th, where it just be a few degrees apart from each other. So on this screen here, this represents tomorrow. We have the members' night. As you can see here, we have lots of targets of opportunity. We have Saturn, we have Jupiter, we also have Mars, which is 17.2 marks, I said, but again, I'll touch a little bit more about Mars because I'm a big fan of Mars for a lot of reasons. Probably like one of the few planets that we have, probably the only planet that can actually see some service details. You have a question?
Yeah, like.
I'm hoping. Right. We'll terraform it too, right? We'll terraform it and hopefully we'll make it more like Earth. But my big plan is, and I tell everyone at work, maybe I can retire on Mars. All right. That's my big plan. That's what I'm hoping for. That's what I'm shooting for. But we got to see what Elon Musk is going to do. Okay. So getting back to here. Okay. So roughly what I said about 8 p.m. Orion will start to rise again. That's another constellation, M42, the Orion Nebula. It's another big favorite of mine because when I started off astronomy, this was the first target I looked at a 3-inch small department type telescope, but it was worth it. Of course, we have the Pleiades up there, M31, Andromeda galaxies, but that's just early in the evening. All right. Next one is the Mercury and Venus. As you can see here, roughly about 4:45. You look at the book. That's the time where they get close enough on the 29th. But you can see here, it's just after sunset. But it'd be kind of nice to have two planets really close together to view it. But we'll see how the weather holds, which I'll talk about in greater detail towards the end. Now the Gemini meteor shower. Again, this is supposed to be the biggest one of the year. which when I looked at the calendar, it says 150, but of course, it doesn't really happen. We'll see how it goes. But we have the full moon to compete with on December the 8th. Next one is the year-sig meteor shower. Just kind of look at Polaris. If you're kind of new to astronomy, you'll get the idea, but don't always look at one point in the sky. Look everywhere because you just never know what's going to happen. It's only 10 meteors per hour, but we have the new moon on December the 23rd. Again, I'll touch more about the weather a little later. It doesn't look promising, but it hits the pre-dawn of December the 22nd would be a good time. 1 p.m. or 1 a.m. or 2 a.m. around there on December the 22nd, which is really close to Christmas. Okay, like I mentioned before, I'm going to talk a little bit more about Mars. Now, what I have up here, and maybe I should grab the laser pointer. Okay, I try to illustrate here the difference between every 2 years we catch up with Mars. And you can see here, the size of Mars varies. And the pattern is, you can see we almost touch the same distance every 2 years, pretty much. Like 2001, we're at this distance here, 2003, 2020, about this distance here, which is not the closest point there. But it kind of gives you the idea that over here, Mars and Earth, you know, kind of like the elliptic pattern of it, we do catch up on it, but not at the same point. That was my point here. We don't always catch up Mars at the same point. So the distance between the two planets varies every 2 years. But there is a small little pattern, which I'll bring up to the next slide. Okay, this probably illustrates a little bit better what I'm trying to say here, is that back in 2018, it was like 24 arcs across. It's not the biggest. I heard it was bigger back in 1990, I think it was, where someone said like a small little telescope and you can map out, draw some of the details of Mars. Okay, so every 2 years, we catch up, but in this case here, we're at 2022, so it's only 17, the book says 17.2 arcs. But then the next 2 years, it drops down to 14. Next 2 years, drops down to 13. And then after that, it starts to pick up a little bit more, where it gets a little bit bigger at 2029. The next biggest date that, or the biggest size that we have for Mars was 2035, would be the next time next year, which is still a long way off, but it would be around roughly about 24 arcs across. So again, that's the pattern of Mars that we have here. Now for the weather, we'll talk, really zap myself there. We'll talk a little bit about the weather here. You have another question? No? Okay. All right. Well, we'll talk about Mars after, okay? Okay. Okay, that's cool. Okay. So the temperature here next week around Tuesday, as you can indicate here, it's going to get pretty warm, close to 0. But as you can see here, it'll just peter down back to normal temperature. Well, -20. I don't know what the wind chill is because I didn't really look at it, but you can see the relative humidity is going to be in the high 80s and 90s. Now for cloud coverage here, yes, unfortunately, I cannot stop weather. We are expecting more snow. So we're only going to have really one good night. I looked at a 16-day forecast, which I'll bring up next time. So you can see here, Wednesday around 12 a.m., we're looking probably the only clear skies that we're going to get right up to Christmas. But we are expecting more snow. That's unfortunately, but because I was hoping for that meteor shower on the 22nd, that it would be clear enough. Now, in these two graphs, I went with the 16-day forecast that maybe we have a better idea what the forecast is going to be like. But unfortunately, again, right up to Christmas, right, it's going to be back down to really -25. And when I mentioned this thing at work, people said, well, that's Winnipeg, right? Right? It's going to be cold. So anyways, now in this graph that I have here, again, this is a cloud coverage in terms of percentage. So like next Wednesday, it's supposed to drop down 0. I don't know. Oh, this is December 2nd. So as you can see here in this part of the graph here, which is going to be the Earth meteor shower here around December the 22nd, as you can see here, it's going to be mostly partly cloudy. So unfortunately, forecast doesn't look good. But what I'm planning to do a little differently is I bought myself a Quest 2 VR goggles. So I'm going to be looking at the stars in VR, okay, when it's cloudy. So I'm going to explore that part region of astronomy, and I'll get back to you guys on that. So that's all I have for December 22nd for What's Up. Thank you.
And to present for What's New will be Dr. Danielle Plood.
Ready. Sorry about this. Oh, shoes are no extra work.
Okay, what are we gonna pull here?
I see what the issue is. I'm sorry.
Yeah, it's okay. Sorry, all right, it's all right, it's all right, it's all right. I said we're glad to have you. Okay.
Sorry, everybody.
And Mike Sarah.
It's just Wednesday.
Okay, just here. Sorry to make that. Where'd you go? Is this yours?
Yeah, you Manitoba. It looks like it. It should
This
be
one here. There we go. Okay. Okay, and I guess that's it, just like that, eh? Okay.
I'll just move that over.
Okay, good.
There you go. Okay. Hello, everyone. I don't think I need a mic. You could, yeah. Should I for the recording?
On the other mic, so you should be.
I should be okay. Okay. Hi, everyone. So today's What's New went on. I was like, I'm going to do a couple things. And then I started reading, and then I went down a rabbit hole, and then I just stayed in the rabbit hole. So that's, I'm sorry. If you thought you've already heard a lot about Mars and the moon, I apologize. So hopefully people had a chance to take a look at the lunar occultation of Mars on Wednesday night. It was very cold. So I did a lot of like running out of my apartment, looking up for 5 minutes, running back in. But it was a really exciting evening. But I will be talking about the moon and our attempt to go back. So this is yesterday's astronomy picture of the day by NASA. So this is the Orion capsule and lunar features. And so if you haven't had a chance yet to look at the new images of the moon that are coming out of the Artemis mission, I highly recommend it. The resolution is incredible and they are stunning. So we have a solar panel here. We can see the ocean of storms. You can see some really lovely detail around the craters and around the terminator. So if you haven't just been absorbed by these photos, I highly recommend going exploring. So Artemis 1 is NASA's attempt to go back on the moon and to re-land on the moon after 50 years. And so Artemis 1 is the first mission to go back since the Apollo missions, with the intent of landing a person on there. It's not the first thing to go back to the moon, but this is the first integrated uncrewed flight test of the Space Launch System, or SLS, and the Orion spacecraft. So right at the nose there, you see the Orion capsule. So this was successfully launched November 16th, 2022. The mission just completed its second lunar flyby, passing 127 kilometers over the surface of the moon. And it is planning on splashing down through our atmosphere into the Pacific Ocean on December 11th. So its mission is coming to a close. And this is a really cool image where you can see both the Earth and the moon in the background. So it's really fun to see these images at kind of modern resolutions. It's really great. All right, so here is the mission to date. So on November 16th, Artemis 1 launched from Florida. So you can see the little number 1 on the globe, right next to where Florida would be. So Artemis came up and around, did a couple lunar flybys in green, transitioning to gray, then to blue, and then following the numbers in order, preparing to splash down. The rabbit hole I went down is that Artemis also carried along 10 CubeSats, which are really small satellites, with it. And so I did a deep dive into each of those and what they were doing. I'm sorry. But I think they're really fascinating. And so they deployed these and they all kind of scattered into different orbits. Scattered is maybe less intentional than what was actually planned, but they all went in different directions and have different science. So it's a really exciting time for kind of small satellite science. So in the words of the NASA Orion review, Orion will serve as the exploration vehicle that will carry the crew to space, provide emergency abort capability, sustain astronauts during their mission, and provide safe re-entry from deep space return velocities. So it's got a heat shield on the front, cold shield in the back, some propulsion mechanisms. So eventually people will go in there. The other side rabbit hole I went down was I really love mission patches and logos and designs. So the ones I could find were there, but a lot of my time went into being like, can I find all of them? The answer is no, but I tried. So both Artemis and Orion have some really nice complementary logos here. All right, so there were CubeSats aboard. So here I have an adapter ring between the SLS and the Orion, and then each of these little slots carries a CubeSat. And so there are 13 slots, only 10 of the CubeSats were delivered on time, so 10 of them got launched. Most of them were 6U CubeSats, and what that means is the 6-unit cube satellite. And CubeSats are defined in units of 10 centimeters. So 1 unit is 10 centimeter by 10 centimeter by 10 centimeter. So you can fit 2 by 3 for a 60-unit or a 6-unit CubeSat. So the total volume of these things are 10 centimeters by 20 centimeters by 30 centimeters. And most of them weigh in the 20 to 30 pound range. So they're pretty light, but they get launched in this adapter ring. And they were set up kind of perilously. Most of them were sent out to test new technologies. But because there was some trouble launching, they had to delay the Artemis launch, the batteries on these small satellites were left to drain. And so they weren't sure whether or not they were going to still have battery by the time they got orbit and were able to expose their solar panels. So for all of those considerations, of the 10 that were successfully launched, 7 of them are completing their orbits as expected and are communicating back to Earth, and 3 of them have not. So I'll go through each of them here. So there are 7 small sat missions that are a success. So those are Argo Moon, BioSentinel, I'm going to butcher this pronunciation, Equulus, feel free to correct me, Luna HMAP, Lunar Ice Cube, CUSP, and Lunar. And then missing in action satellites are Omotenashi, Team Miles, and NEA Scout. So Argo Moon, this is an image of the moon from Argo Moon. This is a NASA Italian Space Agency collaboration. The Italian Space Agency is coming in hot off their success with the last time I was here, I talked about the image of the Didymus landing. So that was the same. The Italian Space Agency was also responsible for that small satellite. So this was injected into a heliocentric orbit. And then, so it started in a heliocentric orbit, and it's going to use a combination of propulsion and lunar flybys to come into a geocentric orbit. And it's going to take detailed images of the interim cryogenic propulsion stage following the Orion separation. And so essentially it's taking pictures of how everything is going to make sure that all of the other small sats are deploying okay and that the separation goes well. So it did that successfully. It also demonstrates the ability of a CubeSat to conduct precise proximity maneuvers in space when other things are still pretty close. And they tested autonomous navigation and long-distance optical communication. with Earth. And so here's an image of somebody working on the small sat. So that's the whole size of it. So you can see somebody's hands for scale. So it's pretty impressive that something that small is hurtling through space. Okay, this one is my favorite. This one is super cool. Okay, so this is BioSentinel. It's a NASA mission, and it is a NASA mission to detect the effects of radiation on DNA and life in not only low / no gravity, but also in high radiation environments. And so it is carrying budding yeast on an 18-month mission to study the effects of radiation in space on life. And so it's the first long-duration biology experiment in deep space. So there have been experiments on the ISS, but that's pretty shielded from radiation. It'll help protect future astronauts from the harmful radiation from space. It will test the exposure to high-energy particles that can damage DNA and cells. And so the reason they picked yeast is that they could dehydrate it and launch it, and then it will essentially be dormant for as long as they need, and then they will rehydrate it when they want to start doing the experiment. And so they have these little microfluid chips, and they have something like 16 of them, and they launch 2 at a time, and then they will rehydrate 2 at a time, like a test and a control. And then every few months, they just rehydrate 2 more. And then they have a matching set here on Earth. And then they have a matching set on the ISS so that they can do the same experiments at the same time to kind of separate the effects of gravity and radiation. So something that's on the ISS will have no radiation and no gravity. Something in space will have radiation but no gravity. And then here on Earth, it'll be no radiation and gravity. So they're kind of testing all of the effects. They also have 2 different strains of yeast, which I think they're depicting here in the purple and the blue. And so they have a regular strain of yeast. I don't remember the Latin name of the specific one, but essentially kind of a natural strain of yeast. And then one that they've genetically modified so that it can't repair its own DNA. And the reason they picked this strain of yeast is because its process for repairing DNA after it's been damaged by radiation is apparently a very similar process to human cells, the way human cells work. And so they have one to being like, okay, this is how human cells or how yeast cells will behave if they can repair themselves in deep space. And then the other one is just like collecting the damage with no reparations. So you can get a real history of the damage. And then they have one pair that they're saving for when there's a solar energetic particle event. So when you're like really extreme radiation. Yeah, so they've picked this yeast because yeast cells have similarities to human cells, including the process of DNA damage and repair. And this will expand our knowledge of radiation risks. So I'm really excited for this experiment. I think this is really well designed and really well thought out. And I'm looking forward to the results for this one. So I'm glad this one is a success. Another success was Aquilius. This is a Japanese aerospace exploration agency. And it is sitting at the L2 or second Lagrange point for the Earth-Moon gravitational system. Yeah, it stands for Equilibrium Lunar Earth Point. You can choose which E's and U's you would like to choose out of these letters. Astronomers really hold tight to their acronyms and will go far out of their way to make them work. But this mission is observing lunar impact flashes. So it's sitting on the L2 point. There's the Earth. The sun is here. Nope, just kidding. Sorry, I'm too used to talking about the sun. The Earth is here, the moon is here, and then L2 is on the far side of both of them. So it's looking at the dark side of the moon and is going to observe flashes of light as things impact the moon. And it's going to also, it's got a little camera on it. And because it's so far away from the Earth, it's going to be able to see UV emission from the Earth's plasmasphere. So the plasmasphere is a region in the magnetosphere that's really dense, and it tends to emit in the UV when it collides with the upper atmosphere. This is also a steam-powered spacecraft, which I thought was charming. So they have something like several liters of water, which they release very slowly and they heat up. And so you just get little vapor jets that they use for navigating. So that's also a proof of concept technology, I think. Another success was Luna HMAP. And so this is a project out of the University of Arizona with a noteworthy badge. And this stands for Polar Hydrogen Mapper. And so this is a mission that's looking for water ice in permanently shadowed polar regions of the moon. So this mission got off to a bit of a rough start, but it's looking promising. So communication is good, but there are propulsion problems. But they have several months worth of power to sort of work through the issue. So it's looking promising for this, and they can still take data while they're sorting this out. And then just to give you, again, an idea of how small these things are, the small sat is in the carry-on on the plane on its way to launch. A very similar mission, which is also a success, is Lunar Ice Cube, and this is out of Moorhead State University. And it's also looking for lunar water ice. It's operational, and it's using water and other volatiles and measuring how much there is at different times, at different locations, and to see whether or not that depends on the composition of the soil on the moon. Another one, which I'm excited about, is the CUSP small sat, and this stands for CubeSat, where this Z and U have been chosen for solar particles. And so this one has been launched, it's orbiting the moon, and so it will sometimes be inside the Earth's magnetosphere and sometimes not. And so it's a demonstration of technology for eventual constellation of space weather missions in heliocentric orbit. And so this one is exciting because in space weather, we do modeling. So like my research background is modeling, where I have information about everything, everywhere, all of the time. And then I compare it to a spacecraft, which is one tiny dot at an instant in time that is moving. And I somehow have to match those. And so when you have a whole constellation of satellites, you now have a much richer information in terms of what things you're doing in multiple different locations at the same time. And it's much easier to compare that to a computer model than a single point in time, because it's hard to separate how things change in space versus how they change in time. So this is a proof of concept, and it will detect both high and low energy solar energetic particles, and it'll measure the strength, direction of the magnetic field. So that one's exciting. And then finally, lunar. This is a demonstrate lunar flyby and remote sensing technology for lunar science. This one is transmitting, but more weakly than expected. So hopefully that gets figured out as well. Okay, in terms of missions that did not quite make it, this one is Omotenashi, which is also from the Japanese aerospace. I'm forgetting the acronym at the moment, but from JAXA. This is also an exemplary 1 badge and 2 attempt at an acronym. So it is an outstanding moon exploration technologies demonstrated by nano semi-hard impactor. So lots of 2 letters from one words and no letters from the other words. They're really stretching it. The word omotenashi in Japanese is like welcome, or like a hospitality thing, which I think is pretty charming for a moon mission when we're trying to go back. But this is demonstrating low-cost technology to land and explore the lunar surface. It also measures the radiation environment near or on the moon. But unfortunately, the communications were unstable from very shortly after the deployment. So this one is considered lost. The other one is Team Miles. And so this is a mission to demonstrate a hybrid plasma thruster, but this one has also been lost. And so it's silent and presumed lost, and it was supposed to fly autonomously. And then finally, the NASA NEA Scout, or Near Earth Asteroid Scout mission. So this one was launched. It was supposed to launch and slowly deploy a solar sail and then use solar radiation to navigate and propulse itself away from the moon and towards a near Earth asteroid. It was going to take lots and lots of images with a 10-centimeter resolution for the target asteroid to give us a really good idea of what the composition of the asteroids were, so that if one was ever directed towards us, are they mostly solid boulders? Are they mostly loose clumps of granite or gravel? And because which one that is will tell us what our best approach is. If should one be directed at us, or if we want to deflect one, we could take different approaches based on its composition. So it's disappointing that this one didn't work out. The solar sail is huge. It's 86 square meters. Yeah, so it was going to be a robotic reconnaissance to meet with a small asteroid in 2023, but there was no communication after deployment. NASA sent the command to unfurl the sails in the hope that if they unfurled, we would be able to see it and then find it and then eventually communicate with it. So as of yesterday, it was supposed to be in the Aries constellation. So if it did unfurl, there's a chance that you would be able to see it reflect some sunlight. If you're looking. And that's it. That's all I've got. So hopefully in the next few months, we'll get some science results from the missions that worked, and we'll learn some things about the ones that didn't. And we'll hear a lot. Well, hopefully this splashdown will be incredible. And it'll be really exciting to follow the Artemis missions as they go forward. Thank you. Any questions? Yeah.
On the Artemis, there's a path on there that's in dotted lines. Is that one that couldn't happen? Yeah, I looked at that on the internet. They didn't mention anything about that.
Yeah, so
I think that's
the dashed line, the booster. Okay. Yeah, because this is the ICPS, the CubeSats deployed, A, B, and C. So there are some CubeSats that are deployed here, some that are deployed here, and then some that are deployed here, I guess, depending on where they want to be for orbits. Yeah. And then I guess the booster would have to kind of get flung out into space. Yeah, Judy.
Do we know whether the 3 that aren't working are the ones that have their batteries run down the most, or any idea?
I'm not sure. I didn't read that. They were all put in the, in their frame. Thank you. Yeah, they were put in their frames at the same time. So I'm not sure if they were designed with different battery sizes or capabilities. They were made by different groups, so there's a chance that that was the case.
too bad.
Yeah, it is too bad. Yeah.
Because they delayed the launch, they went back and recharged the batteries, but they couldn't reach all of the CubeSats, so it's a little but the low battery.
Oh boy. Okay. So
Maybe it recharged over 7.
Okay.
They're kind of waiting on top of that.
Okay. Was everybody able to hear that? Yeah. Okay. No? Yeah, could you hear it? Okay. Okay. Yeah.
The Luna HMAP, the HMAP mapper, I've heard of other folks that can do that. I'm just wondering, how they actually detect hydrogen on the surface of the planet? How does that work?
That's a good question. I'm not sure. I could do some reading during the break and get back to you, but yeah, I'm not sure. The mission website is here though. And so this website was really well laid out. So some of them were really hard to find a lot of detailed information about, but this one, the ones with the badges, did a good job of having a website. So, yeah. Okay. All right.
Great.
Thanks, everyone. I'm just going to eject my.
So we'll take a 10-minute break and then we'll come back for our main presentation.
This works here. Yeah,
There we go. Okay.
I like it. Right click it. Actually, well, if you just go there and right click it, probably.
There we go.
And you just.
Perfect. Thank you.
That was a really great presentation there.
Oh, thank you.
Yeah.
Oh, you can just leave it now. That's
Okay.
but yeah.
Okay, there you go.
Thank you so much.
Okay, thank you.
Thank you.
Thank you.
Now I'm gonna want to go back in and out of PowerPoint and the internet.
Good luck.
I don't know if that still goes through on the Zoom.
It should. Let me just see here. Oh, man.
I mean, on my own computer, it's easy, but this computer has weird things in it.
Really? Okay.
Some of the switches don't work the way they do on mine.
Okay.
As long as Alt Tab works.
That's not. Okay, I'm gonna pray that work.
Be self-evident.
Okay, now, where did it put it?
Not there.
I'm just gonna stop sharing. Give me a minute. Sorry, just give me a minute. I don't know why it's doing this. This started when. Let's cancel. Just give me a minute. Okay, so. Oh, man. Good. Okay, there we go. Okay, come on, let's go. There we go. We should be able, now you said you want to go into that internet, right? So, like, where did I put Chrome? Just give me a minute.
I have links embedded for the internet, so they'll come up when I need them, but.
Yeah.
And they'll probably open up new internet links every time.
It actually, what's going on here? It actually did work.
Yeah, it got moved, I think, when it got unplugged. Is this Danielle or is this Jace?
That's mine.
Yeah,
It's done now. Full of
Yeah,
it.
actually, yeah, sure.
Yeah, okay.
Yeah. Upside down. Yeah.
It's always upside down the first time.
It's always upside down,
Here.
even if it's right side up.
Okay. Why is this? Sorry. Just give me a minute.
It's the webcam. People wanted to make sure that they could see the presenters as well as just their
Do
screen.
it that way.
Yeah, the one problem I have is I'm going out on the internet. I don't know how that'll come out on the Zoom.
It
What do you mean you're going out on the internet?
Well, I'm
Clicking
coming
on
out
the
of
link.
PowerPoint.
Oh, it'll be fun.
It should be fine, yeah. Should work. Are your links in?
Well, my talk,
Deserve.
Oh, am I? Shoot.
How you doing?
I don't want to even shut that off right now.
Okay, yeah.
Where, can we just test one?
Yeah, well, let's see where it is. It'll be in
In here maybe, or?
somewhere, go up to the one above it, somewhere in there.
Oh, no.
Just keep scrolling down.
Oh, my freaking $1,000.
I have to see it on. I forgot, they're bedded in several places. Go down one more, I
Fantastic.
think it's there. Just do that.
Control and click.
It's going to get there. You don't want to walk.
Okay.
There you go. Yeah, you're good. Okay.
I had to
Right.
replace the door.
Yeah.
I don't know, they got in, they went into the gazebo. I had a little.
Yeah.
He took a photo.
Would you like to sign this card for Brian?
Oh, yes. Yes, it would. Actually, that would be good. Okay. Thank you.
The door, of the door.
Official cards.
I reported that, that was an adventure in itself. I go all the way,
Yeah, thank you very much for doing that. That's great. Yeah.
There's one downtown, and then there's one in the way down Grand. There's another more in the press. But I went all the way there to find out that they're not open to the public. How do you have a police station that is not open to them? I finally got through.
You might be able to zoom out. Does it
Yeah, I
have
was
a?
kind of wondering what that does. Yeah.
Safe to me.
Was that just focus? Hey, Stan.
It's a manual focus, but it doesn't. If you click on the properties of it, you might be able to zoom out. I don't know.
How you doing there?
Okay.
Ben?
Properties of that, okay.
You like it here or
so-
just learning?
Oh,
See, it's actually out of focus right now.
yeah. Well, I turned it and then I didn't focus it properly, apparently.
Okay.
When I'm up there, I like to have it out of focus. It makes me look better.
Yeah, it's all right. That's what you're trying to catch.
Yeah. But it's a pretty
Yeah, so
narrow
if they
field.
kind of stand here and then it's good.
Right up.
Yeah, you need a wider field of view.
speaker tonight is gonna be talking to us about making day into night. And it's our very own Jay Anderson. Jay?
Thanks, everyone. I've already had one question. What the heck do you mean by that title? Well, it means that you're going to spend the daytime looking at a computer and evaluating the weather so that you know whether or not you can go out at night. I think when I started to put this, the first time I typed weather in, I put an H in there. And I think that would be more appropriate for weather forecasting. For those of you who don't know, I'm a retired forecaster. I worked for a number of years with Environment Canada, and it's like a bicycle. Once you've learned it, you never stop learning, and you can always ride a bicycle. And if you've been a forecaster, you can always write a forecast. Okay, now let's see. Remember I told you how this computer was different? Well, it doesn't respond to the keys to go forward. So let's see what we can do. Not that one.
You know, just click that.
Oh, you want me to work on the mouse?
No, that's not working. Sorry. What about this one? There you go.
Okay.
Just page down, page up.
Hit the number 3, obviously. Okay. Well, we've only been interested in 3 things when it comes to astronomy as far as the weather's concerned. Well, maybe 4 if you're sensitive to temperature. Everybody's saying how cold it was to watch the occultation of Mars the other night. I thought it was quite warm, actually. I was pleasantly surprised, and temperature came up 5 degrees while I was watching. So, yeah, -20 is not really cold for doing astronomy in this country. So anyway, I'm going to cover cloud cover, seeing, and transparency. And we're going to talk about where you can get information about them. Most of you know some of those sites, but I want to get you a little bit deeper into it a little bit by showing you that by going to these online sites like Clear Sky Clock and Skippy Sky and a few of the others, that you may not necessarily be getting the best information that you can. I want to talk about computer models first, because so much of what we do is based on computer modeling. So when you want to write a forecast and run it through a computer, you have to have a place to do your calculations. And what they do is they divide the world up into a grid. And you can see here in this sketch that I've got here that you have a grid that covers the surface of the Earth. And that grid can be quite extensive. It depends on your accuracy and your resolution in your model, how much detail you see by how closely spaced those grid points are. But those grid points also have a depth. They're not just one layer across the Earth. They're layers at many, many levels up into the sky. You can get models that cover the whole of the Earth, and you can get models that cover smaller areas of the Earth, domains as we call them. And some of you are familiar with the model known as the North American model. That tells you exactly what the domain of that model is. Now, these parameters in the horizontal, you can see I have a diagram here on the left, and I show layers in the atmosphere, but also layers in the ocean. And the atmospheric model is coupled with other models that do other forecasting. So we actually have a marine model that forecasts the quote weather unquote in the ocean, currents and the way they change. We have models for ice. We have models for land that involve the land cover and the albedo of the land and whether it's snow covered and things like that. And these are coupled into the atmospheric model. So you're not actually looking at one model when you're looking at a forecast. You're looking at sometimes as many as 4 different models. And of course, each of those models has to have its own inputs and outputs. So if you're going to have a model that looks at the landscape, you have to know where there's snow on the landscape and whether or not that snow melts during the day, because if it does, it's going to change a forecast in the afternoon from one in the morning and so on. The GFS model, which is the global forecast system, that's the name of it. It's one we use quite a bit for long range forecasting. It has 127 layers in the vertical. That's a change from 64 layers that it had just a year and a half ago. So they've obviously got themselves a faster supercomputer that they can now put more layers into the atmosphere. And with that, they can sort of get a higher resolution. You'll see here on the left-hand side, we have a lot of the layers are spread out in the middle, and they're very compressed down here at the surface, and they're compressed up at the upper levels of the atmosphere, which is up and around the 40,000 foot mark. We measure layers as pressure units. So these are 1,000 millibar here and essentially 0, which would be space. So when you put all of these together, the number of grid points and the number of layers, you end up with having to do calculations at about 32 million points to cover the globe. It's actually an overestimate because as you go further out in time, they reduce the number of grid points and make them cover a wider area. And later on, we'll give you some examples of just where or just what those grid points are, what their resolution is. So when we do run a fine scale model, it's nested inside a global model. You have a problem if you're running a computer model that has an edge to it, is that as you do your calculations, things on the edge start to come into the middle of it, and you don't know what the conditions are on the outside of the edge. Sometimes you say, well, everything on the, that's beyond the edge is identical what's inside the edge, which is not a really good way to do a forecast. So even with any kind of a model, they lose accuracy as time goes on. And so there's a limit to how far out you can go in the future. Currently, with the GFS model, it's 16 days, but it's not particularly reliable in my mind beyond about 5 days, other than to give a general indication. So when we have a model such as the NAM model, the North American model, it sits inside the GFS model. And as time goes on, the GFS model is passing stuff into the NAM, and then the NAM begins to do the calculations at a much higher resolution. You want to know what the equations are? This is the basic equations. They're called the primitive equations. And if you know your math, if you really know your math, then you'll be able to understand these. And I can think of perhaps 4 people in here that could follow something for this. But they're actually quite simple in concept. You're understanding it too, are you? Okay. No, but you will someday. If you're going to be an astronomer, you'll know exactly what these mean. We have these 2 components of momentum. Basically, what they say is you're looking in one of these little boxes, and it says you're borrowing wind speed from the box beside you. We do that. And what's the weather in Winnipeg tomorrow? Well, it's the winter or the weather in Regina today. It's actually more accurate to say that it's actually in the weather in Melville rather than Regina. We've tested that, and our weather tends to come more from that direction. Anyway, they have one box. So what do you got? What's the wind going to change? Well, it's going to be the wind you've got, plus something coming in from the side, something coming in from the other side, something coming in from north, and everything going out in those directions. And what these doing is just putting all of those. There's also a term, this little one right here, that's for a force that's created by the rotation of the Earth. And this is a force that is related to temperature changes that occur. And this is the force of friction if you happen to be at a layer that's close to the ground. And you get those for U and V components of the wind. And you have to do that because when you're calculating with something that has a wind in it, you have a really big problem with the wind, because once it gets to 360 degrees, the next wind direction is 0. And when you start doing mathematical calculations, you can't suddenly go from 360 to 0 without causing some great big discontinuity. So what they do is you say, well, we'll break it into a north-south wind and an east-west wind, and that's what these U's and V's are. We have continuity equations. Those are things that just stop you from piling up all of the mass in one grid box. If it's coming in, it's got to go out, or it's got to change the density. Thermodynamic equation just takes care of temperature as it moves in and out of these boxes. And moisture takes care of moisture. And the hydrostatic equation just makes sure that the pressure at any one level in the atmosphere is equal to the weight of the atmosphere above it. And you don't suddenly end up with a big pile of extra mass at one point that all of a sudden you get a big jump in pressure. Pretty simple. These only predict what we call the dynamic parts of the weather. They don't predict cloud, they don't predict humidity, they don't predict windstorms and tornadoes and thunderstorms. All they do is predict the way the wind is going to flow. And these models have to stop every now and then and calculate all those other parameters. So everything is coming in and out of a box just like this. And all those terms are just to keep track of all those parts as they come out. So you do that for each one of the 32 million boxes. And then you step ahead a small time step and you do it all over again. And the whole thing looks like this. First, you create a 6-hour forecast from the previous model. And you use that as your template to start. And then you initialize it, which means you take all of the data that you've collected, the satellite observations, the measurements from the balloons, measurements from the ground, radar observations, and you put them into this 6-hour forecast. And you're going to have places where they don't fit. You've made a mistake, there's something wrong in your calculation, so you then bias the model. And up to fairly recently, and maybe still, that was done by hand. People would say, well, the wind over Alaska is predicted to be 35 knots, and it's actually 55. So I'm going to put in a 55 knot wind there. But the minute you do that, that means all of your calculations of temperature and pressure and the wind have to change to keep that wind valid. Otherwise, the model just throw it out again. So it gets to be quite a complicated process. But once you've done that biasing, you then begin to solve all of those primitive equations and you obtain the T0 forecast, the starting forecast. And from that, you step ahead, in the case of the GFS model, 7.5 minutes into the future, and you calculate everything all over again using the forecast that you just had from the first time. And you go ahead and do that again and again and again until you run out to 36 hours. And after that, you take a bigger time step and you go out to the 15 days. And every now and then you pause. And by every now and then, at least hourly, you pause and you calculate all these other things that you want. I know the wind, I know the temperature, I know the humidity. Oh, humidity here has gone up to 70%. I'm going to start making clouds there. And then, oh, it's gone up to 95% here. I'm going to start dropping rain out. Those are just simple ways of doing it. They're actually much more complicated than that. But you have to calculate all these other parameters that go into the forecast because nobody wants a forecast that says, well, 950 millibar wind is 35 knots out of the southwest, unless you're a pilot. So you want to know, is it going to rain? Is it going to be snow? Is it going to be windy? Is it going to be thunderstorms? And all of that stuff has to be calculated from the solutions of these primitive equations. After about 4 hours, the forecasters out in the field are getting antsy and they want that new forecast. So it's sent out to them at that point. So all of these, approximately 1 trillion calculations, are all done within 4 hours. And the first forecast goes out to the forecasters. Well, these forecasts are done every 6 hours in most cases of these models. Some of them are done every hour, but they're very limited domain. Other ones are done every 12 hours. Canadian ones are done every 12. American ones are done every 6. So you start over again. You start over again by calculating a new T0. And that T0 has got all the information in it that has been coming in during the 4 hours that you were doing the forecast. So the second time you calculate that T0, you get a more accurate forecast. And that's the one that's archived. So if you want to go back in time and see what the forecast was or what the weather was, not the forecast, you'll have that T0 file. Gets complicated. Well, many of us use what I call spotweather.com, and I'll talk about that later. And the only reason I'm in this page is because it tells you, spot weather gives you all of these models down the side, which are listed here, to be able to make your forecast or to see the forecast. And some of them you want. You can see the names, the RDPS and the GDPS right here. These are the main Canadian models, the regional deterministic prediction system. Canadians like to have really crazy names for their files. The Americans are more simple, North American model or the global forecast system. So these ones, the NAM and the GFS in the US are the same as the RDPS and GDPS in Canada, the same sort of model. They use different equations, and so it's reasonable to compare the two of them to see where they agree. The HRR here, the HRRR, is usually for thunderstorm forecasting, and storm chasers use that. And we also use the RAP when we want to do the HRR is generated every hour. But it just covers centered North America, about as far north as Gimli. And the RAP is pretty much the same. It's generated every 2 to 3 hours. The times change according to whether it's the middle of the day or whether it's overnight, because it's designed for forecasting for severe thunderstorms. Brian showed a global ensemble. He didn't mention it, but one of his models. What these are is you can change the initial conditions in one of these models and run it over again and see if you get the same answer. And so that's what they'll do. They'll change a few little parameters, the old butterfly wings that are flapping, and they'll run the model again. And what they'll do is they look at the range of answers they get. So in the diagram Brian showed in the GEPS model, let's see if this works. I think I have to get out of my laser pointer here. All right, well, we'll just do this the hard way. All right. I hate keyboards that give me. So here's your spotweather.com, the ones I was going to show you. This has all the names of the files. Right now it's centered on top of Winnipeg. And if I go and select down here my forecast here, you can see the list of all the models. So I want to say, look at the NAM model here. And there I get the kind of graph that Brian was showing us earlier on. We can then go and look at this, what's called the ensemble forecast here. This is a forecast that represents all those different model runs. It shows you the range of answers that you can get. So if you want to have some idea of how reliable the forecast is, you can see we have a temperature here, we have a relative humidity. You can see as you go out in time, especially after the first 3 days, those areas get broader because the accuracy becomes less. And you can look at the precipitation forecast, wind speed stuff, sea level visibility, and so on. These are all extra parameters that are calculated out of these models.
Jay, have they taken a look back and said, okay, how, when they say it's this range and they actually get the weather, do they look back and say how accurate?
Always. They know every grid point, how accurate it is. I mean, you couldn't really make improvements unless you did that.
What's the penalty for an inaccurate forecasting?
In the weather office, when I left it, individual forecasters were verified. In other words, we knew who the best forecaster in the office was and who the worst one was, and we let them know. So every 3 months you would have a assessment, and quite often the person who was worst one time would turn out to be the best or second best the next time.
Is the accuracy related to weather monitoring stations? Is the accuracy related to weather monitoring stations?
Well, of course it is, but it's actually probably in a lot of parameters verified against the T0 archive model, because you won't always have an upper air sounding to tell you how accurate your forecast is at the higher levels. Anyway, let me just. I hate. So let me just. I always got to learn new positions here for these things. So this is just an idea of what you can get. Now you can look at other displays. This is a outfit called Pivotal Weather. This is an important point in here. These are the same forecast at almost the same time, all of them, for 6 different models. You can see SRAF, I didn't cover that. It's just another one of the models out there. The GFS, the HER, the NAM model, GDPS, and the RDPS.
Which line is that?
So let me just get.
From what site?
This is, you can go to Pivotal Weather. You see it's written in there, Pivotal Weather. That's, I believe I might have an address for it at the end. Let me get my pointer up here. Come on, mouse, where are you? There we go. Okay, well, let's take a look in here. You can see in this model, we have a gap in the cloud cover right here. Blue generally means very little cloud cover. Here's the same one over here, the GFS model. It's not the same, but it's not entirely different. The HER model doesn't really go far enough north, so it's not doing anything. The NAM model, which is one I like to use a lot, not very different than this one, but not very similar to this one in the details. The cloud covers come in a little farther. If you were saying, well, can I observe successfully in Winnipeg? If you look at the GDPS here from the Canadian model, it's kind of iffy. You're right near the cloud edge. If you look in the RDPS, also the Canadian model, I should point out the RDPS and the GDPS use the same equations. They just, one's a higher resolution than the other. Well, how about if we cover that off later? If you wanted to observe in Winnipeg, you could look at all 6 of these and say, I look pretty good.
What site is that?
This is for last Monday at 6 a.m.
What site is it?
Pivotal Weather.
Oh, Pivotal Weather. It's written on it. In every one of them. Pivotal Weather, Pivotal Weather, Pivotal Weather. I don't know. You go to pivotalweather.com. There are many of these. The thing is first of all, they all use the same models. They'll use the GFS. They'll use some of them. You'll find they use a British model and a French model and everything else. You can get modeled to death on this. And so if you wanted to go observing in North Dakota, you might have a little more of a challenge because this one says, hey, you're fine. This one says, don't go to the south. This one says, you're only good up in the northeast corner. This one says, you're not good anywhere. This one says, you might be and you might not be. And this one says, yeah, but it's kind of thin. Which one are you going to use? So don't use a whole bunch of models. Use 1 or 2 models for the long range. Use 1 or 2 models for the short range. Learn to what they can do for you. You can have this ensemble. This is one that combines one of those, a whole bunch of different predictions and sees all of things and gives you the average. This one says, hey, North Dakota is mostly good. Winnipeg is mostly good. How good is having a whole bunch of things that aren't very accurate averaged out make something more accurate? Often it does. The point is, if you have something critical, you can go to one of the areas where everybody agrees or almost everybody agrees with a reasonable certainty that they're right, as long as you're not too far out into the future. Well, here's what it looked like. First of all, North Dakota is a complete washout. So none of the models are right in North Dakota, except maybe one that had. Which one had North Dakota over here? This one, the NAM model, pretty much wiped out Nova Scotia. Winnipeg, it's hard to tell because it's an infrared image, but this area through here is mostly clear. There's a batch of cloud in here over Northwest Ontario. This is cloud coming down out of the north and a little bit over here. And when you go back and look, most of them don't go. But for the most part, this thing is a little farther southward on all of the models. We have a saying in the weather office that the models look more like each other than they do for the weather. In other words, picking one model and looking at the weather and seeing where it makes its errors is probably going to be farther ahead than looking at a bunch of models. Here's another example. This comes out of the College of DuPage website, which I'll talk about. And you can see that we have different days. We have a nice big clearing. This is the prediction. And this one is I don't think I can quite read the top of this. I got all of the stuff from Zoom on top, so I can't read it, but I think this is about the next day. So what we have here is quite a bit of cloud out to the south, but Winnipeg looks pretty good. And then we'll go and take a look at it. We can see that here's this cloud I've got circled up here on the top. This is the big heavy cloud over Lake Superior. And if you go back, you can see that it's actually moved quite a bit farther. It's up here. This is holding it way too slow. This is a 36-hour forecast. And you look down in here, this is all fog and low stratus in through here. So it's cloudy from Lake Superior right down across South Dakota here. And when you look at the model, it also has it cloudy, given that this is too slow and moving, it's cloudy over, there's not enough cloud. Thing is, you don't know from this model that this stuff over the lake is high level cloud and this stuff on here is low level cloud. It's not telling you, just telling you that it's cloudy. And it makes a difference because if you go to the edges of this one, it's going to clear out, and that may or may not happen here. So you have to be a little bit aware of how things might be moving and try and get some additional information. There are models that will give you cloud levels, but I don't really like them. We've had a look at the spot weather thing. This is just an example here. These are two models here. We're looking at, I think, the NAM model here and the RDPS. So they're pretty much the same types of models, but look at the differences they have for the same time period. GFS tends to be colder. You can see that when you get up into Wednesday morning. So what could you say about the weather? Well, it could be cold Wednesday morning, could be minus 22, or it could end up being minus 36. Well, I know that this model, I wish I could read that. I think it's the NAM. The NAM model tends to be cold. After a while, you learn that. You say, okay, I'm going to go more with the GFS model because temperatures tend to be a little more reasonable. Minus 36 is record territory and models that forecast records. Now, the reason they do that is because when your actual forecast comes out, they take the model forecast, but they apply a lot of statistical and other corrections to it to get it to be a little bit more accurate. We can see that both of these models have precipitation. Long way. In here, they're looking at about 2 millimeters of precipitation. This was Tuesday night last, and that looked okay. At least they agreed. And in fact, they were right. We did get precipitation. I think it was about 10 centimeters of precipitation. So yeah, it's going to snow. We got the amount a little off. Well, I might just, if we have time, I might just show you some ways of getting it. Be skeptical. Be skeptical. And especially if you want to go out more than 5 days, You want to say, well, I'm just going to look at the trend of temperature. Is it going up or is it going down? Is the weather going to go to a long period of sunshine? Or is it going to be up and down? You won't believe each up and each down in terms of cloud cover, but you'll know that we're going to be in and out of cloud, and that's probably reasonable. The other thing is that this model tends to put in 100% cloud cover whenever it starts making cloud, and the other one, maybe I did a bad example here, but one of them, the Canadian model, tends to show cloud going up and down, a more realistic representation of cloud instead of just putting everything. A lot of us use Clear Sky Clock. This is based on the RDPS model. So you're basically just getting a replay of the RDPS model, but with somebody else's idea of how to calculate the cloud. I hope you know that if you click on any one of these boxes, it'll pop up a map for you. So you can look at the whole of North America with this kind of detail on it. Clear Sky Clock goes beyond just cloud cover. And you see that up here in the showing cloudy Friday night. So I guess that's working out. It's got transparency and seeing. Darkness is handy, but that's just kind of a administrative thing. You want to go out when it's dark, and it sort of tells you when the moon's out of the way. And smoke, wind, humidity, and temperature are sometimes important and sometimes not important. It's transparency, which is calculated strictly from the amount of moisture in the atmosphere, and seeing, which based on wind and wind shear, that is the way wind changes with height. And it's also got some surface temperature changes in it, because as temperature falls at night, things tend to get stable. And so they just put that in as a predictor. So seeing is what I want to cover next. It's turbulence in the atmosphere. And there are 4 places that you get it from, which are well known to most of us, where it comes from. Some we can control, such as local stuff in our own observatories. We try to cool the telescopes down. We cool the observatory down. If we're out in the open, we give the telescopes time to equilibrate with the outside temperature. The turbulence comes at the number of levels, and when they calculate it in the Clear Sky Clock, they just do a summary, a sort of integration through all of the levels. We get these thermal irregularities, little sort of high density, low density areas in the atmosphere that can be anywhere from this big across to the size of the biggest telescopes. And that's what gives a little bit of the bounce on the bubbling in our seeing. You can use the Clear Sky Clock, but you can also get some ideas on other places by looking at these individual factors. So here is clicking on one of the Clear Sky Clock boxes, and this is the kind of thing that you come out with. And you can see where instability is low, or seeing is good, where the turbulence is low, the instability. And you can see places, well, anything white is cloud covered, and this gray stuff means that the turbulence is pretty high. So what could we use out of the models? Well, we can use measurements of instability, because when you're forecasting thunderstorms, you need to know the instability, and there are many indices in the models that give you instability or stability indexes, and you can use them. They're not so good in the winter, but they're good in the summer. Lapse rates, you want to know how rapidly the temperature falls as you go up in the atmosphere. The more rapidly it falls, the more unstable the air is, because it's going to want to turn over to try and warm it up in the upper layers. I like that one, actually. You want to look at surface temperatures, but I don't find that particularly valuable, because we're so local when we're doing astronomy. If you've got a big temperature change coming in, it's usually a front. And if it's a front, it probably has cloud, and it's going to have wind and everything else. So it's not that useful. If the jet stream sometimes is useful, although you can get laminar flows in the air aloft, where the air just flows smoothly at one level, and you can get very turbulent flows, and it tends to be turbulent around a jet stream. and the same with surface winds. So you might want to look at wind gusts in the models. So if you're close to the edge of a jet stream, you might want to say, well, I might not have a really steady night tonight because the jet stream has got the turbulence that you encounter when you're flying sometimes, and particularly on the edges of the jet stream. If you have the lapse rate, which is the rate at which temperature falls in the atmosphere, if that's high, you're going to be unstable. And the models will give us both a low level and a high level lapse rate. And I like the low level one because that tells me what's happening in the lowest 1.5 kilometers of the atmosphere. Surface temperatures, where this is around lakes. Now, right now, before the lake froze, if you went and observed over the lake, you'd have cold air on the land and warm air over the lake and all kinds of turbulence. But if you go to the opposite situation in the spring where the land is warm, but the lake is still cold and even has ice on it, you suddenly have a very stable layer looking out across that lake. So if you wanted early pictures of the sun coming up and that sort of thing, or if you've got a warm night and you want some nice stable air to look through for planetary photography and things like that, then shooting over a cold lake. Big Bear Solar Observatory in California was built on a peninsula or pier sticking out in the lake so that it was always surrounded by cooler water during the daytime so it could get the solar images it wanted. Model instability values. Well, let's just take a look at some of these. Here's at the top, we have a jet stream chart. You can look in Winnipeg and see this red area. There is a scale with these, but it's down here in the bottom. And these are in nautical miles. Or knots, nautical miles per hour. So we can see it's relatively windy here. We're showing 120 knots or something like that, much higher in here. This is typical of winter, 150 knots. So 150 knots is what, 250 kilometer an hour wind, something like that. Double it and subtract 10%. Except at that level, they take more than 10%. But anyway, it's pretty turbulent up there, and you're probably not going to get the best seeing. But if you watch the models over a period of time, this will probably move off and you get into the lighter winds here. In this case, we're looking at an instability index, and at this time of year, there's no instability here, so you have to look farther south. Basically, these green and yellow values are high. They're going to be areas that are full of some kind of cloud. What you want to do is look at these areas out on the edges. I like that better in winter at night because all the afternoon instability settle down, but you'll see where there's still areas that have more than the other, and that will show you areas that have a tendency to be a little more seeing disturbed. And this is just another kind of stability index, but I've zoomed in here because I want to look at Florida right here. And you can see there are some areas in here where the instability is very low, whereas over here in the water where the Gulf Stream is and it's warm, you got a higher level of it. You got some more on the Caribbean side, and of course big weather systems over here. But down through the middle of Florida and little pockets here and here, there are some areas of more stable air. But over here, I've got the low-level lapse rate, how rapidly the temperature falls as you go up, and it's given in units of degrees Celsius per kilometer. So here where it's gray, you're looking at about 6 degrees. So temperature after rises 1 kilometer in the atmosphere, temperature falls 6 degrees. That's pretty stable. Back in here, it's falling 11 and 12 degrees under the really, none of those are here. We're mostly get down to about 9. But look at what we see on Florida here. We see reasonably high levels. Now this is at noon, so it's an afternoon situation. So you see high levels over Florida, except right here at Lake Okeechobee. So the lake is stabilized. The model has enough resolution to see the lake and show you that the instability over the lake is less than anywhere else. Now, Mike had a conversation with a fellow in Florida about this sort of thing, and we looked at this kind of chart and the stability charts, and I said to him, you know, from what I see in this time of year in Florida, you want to be inland to watch. And sure enough, his Florida contact confirmed that You definitely want to be as far inland as you can get in Florida in the winter, where these kind of charts show the lowest levels of instability. And so I like this low level lapse rate. You can also get a mid-level lapse rate, which will take you up to about 20,000 feet. I think it's got a lower impact on things. Now, I've also called up the spot weather for a site in Florida, just to sort of look, we need to plan a couple of nights to go out and do some photography of the planets. So which night looks best? And each one of these things, I've sort of outlined areas that look good. So when we look at the temperature here, I've picked the areas with the lowest temperatures. This is Saturday night and Sunday night, this Saturday and Sunday. I look at the precipitation and clouds. Those are two areas that are expected to be clear. I look at the wind and pressure. Well, it's a little windy on this day. Not very much. I mean, we're only showing about 10 knots, but it's lower over here. They're probably both good nights, but this is a better night. And this is also a light wind day, but there's a little more cloud cover that night and temperatures are still low. Here I've got a measurement of instability. This is what's called a lifted index. And unfortunately, it's caught here, but lifted index is just a temperature difference between two layers in the atmosphere. So when this is low, a value of 5, which is shown here, that's very stable, because unstable is a value of -5. But the lifted index is also low here and here. And when you look down, this is another measurement of humidity. It's both low and here, although this, you can see what the scores are. This is called CAPE. You ignore the blue line. So it's a red line you're interested. They're both flatlining there. So from an instability point of view, these are both good nights. Now look at the boundary layer ventilation. Well, you don't worry about that too much. It basically tells you when it heats up during the day, if you have smog, the ventilation tells you how much that'll spread through the atmosphere. So you want the nights when everything settles down and the ventilation is as low as possible. And it happens commonly every night, so that should be all right. And then we go look at the low level wind. And so given all of these, there's no big distinguishing characteristic except the wind over here. So I would say, well, Sunday night looks slightly better than Saturday night, partly because right here in the middle of the night, you'll see we've got we're showing wind and wind gusts in here. So it looks like it's going to be windy and turbulent. You've also got it over here, but your wind is your low level wind is just slightly lower. It's a toss up with the weather, but you wouldn't want to go out on Friday night when you got 2 other nights coming up that look better, assuming that you want to follow this forecast. Transparency depends on moisture and whether or not you have aerosols, and some of the websites include smoke in their forecasted transparency, but smoke models are very poor at this point, so you may or may not be far enough ahead to get it. And this one, there are 2 ways. You can go at it in the numerical models and look at the moisture content of the air. And here's over here on this side, we have the clear sky clock measurement of transparency. Of course, anything with white is cloud in it. So we look like we have good transparency here in southern Alberta. Now, this is just based on integrated moisture, but in the models, you can get this thing called the accumulated precipitation, which is the amount of moisture in the air. If you took it all out and dumped it, how much thicker layer would it be at the surface? Well, we don't get much here in Winnipeg at this time of year. It's about 1/10 of a millimeter if you took all of the moisture out of the air at these temperatures. But you can see that there's a high layer in here that stretches up into South Dakota. Well, that's actually associated with this cloud here, so it doesn't tell you anything. You want to look in the areas that don't have cloud, northern Manitoba, but more likely in Alberta and Saskatchewan, and you can see that we have this dry air. You can see the colors down here, so very dry air coming all the way up through Idaho, through Montana, into Alberta and southern Saskatchewan in here. And if you look, the best conditions are shown to be in southern Alberta here. And it's just as dry in southern Saskatchewan. So there are sort of signs that he's trying to make it a little bit better. So one or the other might do the trick for you. But if somebody's going to do the calculation, then you might as well go with clear sky clock. But you could look back at the precipitable water to see whether they go along with it. More important to us is satellite. And I'm just going to say a little bit about how satellites take. This is on the top, the emission from the sun, and this is the emission from the earth. At different scales here, because on the same scale, this emission would be a very tiny little bump. But basically, the energy from the sun comes in at visible, some ultraviolet, and some near infrared wavelengths here. Hydrogen alpha wavelength is about in here. So we've got a little bit into the near infrared. But beyond that, the sun has very little emission. And so when you look at the Earth, you get this, what's called thermal infrared, up around the 10 micron levels. And when you look at, you can see all these little dips in it. These are places where the atmosphere absorbs incoming light or absorbs outgoing light. And when you break them down, you can see there are areas here, here, and here, and here, and a big one here, and a huge one here, where the atmosphere absorbs the radiation. And you can see what causes it. This is all water vapor for the most part. This is also water vapor because here's the water vapor absorption and so on. So water vapor is very important for the absorption, but there's also carbon dioxide here that creates little bumps over on this one. And you can see lesser contributions. So if you want to look at how much water vapor there is in the atmosphere, you want to look in those wavelengths. And if you look at a wavelength right here, the absorption is so strong, you're only going to see the top of the atmosphere. And if you look here, the absorption is a little less, then you can get down to the middle levels. And if you go to an area that's right down close to the edge of this absorption band, you can see down close to the surface. And in fact, if you look here, you can see right down to the surface. And those are where the wavelengths are that you see on your television every night when they're showing the satellite picture. They're looking in this, what we call a window region, where there's very little absorption. So what that means is you can get a satellite picture like this, which is showing the high level water vapor. It's taken in that wavelength that just shows what's happening at the top of the atmosphere. And this is beautiful for seeing short-term measurements in water vapor. Because if you want to go observing, you want to get one of these dark blue areas over you, or especially dark in here. And when it gets really, really low, like down here around Cuba, it turns yellow. And the temperature scale is on these things. You can watch them move. I'm going to go out to my, we'll just dial this up. This, I get my stuff from, I guess I better type a little better than that. From College of DuPage, and you go into here and you look at satellite and radar images, and up comes the infrared image in that window region that I told you, and they color it up and they ruin everything when they do that. But look down here, upper level water vapor. And there's tonight's upper level water vapor image. Now, if you're in Alberta on the Saskatchewan border here, you've got yourself a pretty nice, well, better than anybody else, transparency. This is very reliable. These things move. Where is my? You can watch them move and evolve, and you can plan, hey, it's getting better in here. If I lived in southwestern Saskatchewan, I've got this nice dry area moving over top of me. I could make plans to go and do something that requires several hours of really good transparency or better transparency. See, this is water vapor, but not all of it is cloud. Just the thicker parts of it are actual cloud, like this here, stuff that's over us. This little hook tells you there's a low pressure system in here that's moving up toward us. But you can see down in here, there's streamers of this lower stuff, and that's because these are along the jet stream. So you run that sort of double whammy here. A lot of the driest air is on the north side of the jet stream, but the jet stream brings in turbulence. So you kind of have to find something that's like this. But you get a night of 4 hours of really good transparency, and then it collapses on you. More often than not, it's one of these little gaps in the water vapor, that the dry area. Now you're only looking at the very highest levels here, but in my experience, that what you see in high levels is also very similar to what you see in the lower levels. So let's just, this guy's loading up here. You can see that the water vapor is more dramatic in the lower level. So there's some high level moisture, or more high level moisture up here in Saskatchewan in the higher levels than there is in the mid levels. And you can go down to the low levels too, but I haven't found the low levels make too much difference on things. So you can do some short range planning. You can see one of these things going over, saying it's going to hit me at the right moment tonight. I want to do some of my best photography tonight. I want to do some of my best observing tonight. I want to go and look for the faintest galaxies while one of these little streams of low humidity is over top of me. And the resolution in this is way better than any computer model. And you don't have to guess whether it's right or not, because you're looking at it directly. So water vapor images for short-term planning, for what you're going to do tonight, because it's not very good for tomorrow night, you can look at the computer models of the upper level humidity and see how good they are. But if you want to know what the actual values are, hey, from 9 o'clock until 1 o'clock in the morning, I look pretty good tonight. And after that, I'll go to some other kind of photography. This really works if you do wide angle photography, where you're just on a tripod. You get those really transparent nights. Never remember which one of these is. So here we are with the water vapor images. So here we are in summer too. For cloud cover, don't look at too many models. I like the GFS and the GDPS, work them against each other. Those are the two long range models from Canada and the US. And I like the NAM and the RDPS for short range out to about 80 hours. So 2.5 to 3 days, 3.5 days for the short range models, which have the higher resolution. Use the point forecasts. They're okay for telling you where your observatory is, but they don't allow you to explore the way, if you're willing to travel an eclipse, a lunar eclipse or something like that. They don't tell you much beyond your own site. You can go click on a bunch of sites and look around if you want on that. Transparency, well, you've seen that, but there are also apps, Clear Sky Clock, Astropheric, Skippy Sky are 3 that I found, and you'll find those will also give you an opinion, and they won't always agree. In fact, more than likely not, they disagree, so then you're left with a dilemma, which one am I going to believe? So pick one and learn whether it's reliable or not. They won't be that different because they're using the same models, although with Skippy Sky, you can change your model. And the guys at Astrospheric seem to be more interested in having more models than anybody else than in exactly what it is they're doing in the calculation. And in seeing, check out some of those parameters that I showed you, but especially keep an eye on the low level lapse rate, which is good for any time except when you're in the dead of winter, because our low level lapse rate right now is virtually 0. The temperature doesn't change very much, at least in the lower layers of the atmosphere. So there you have it. And get all that stuff working for you, and you can do your best photography or your best viewing, your best sketching.
Go back to the previous screen, please.
This will be online, of course, so you can go back and review it if you want and play with these. And for those of you, here are some of the links that you'll want to find these things and explore them. But don't get caught up in too many choices. It's like going to the ice cream store and trying to decide what flavor you want, which one's the best one. And yet that's one thing about the models. There is no best model. Today it's one, tomorrow it's another. Most days, none of them are completely on. But once you're within 3 days, you can generally make some pretty decent planning decisions. So thank you. Do we have any questions?
Is it harder to predict the weather? Is it harder to predict the weather?
Weather predictions are easy. It's correct weather predictions that are hard. I mean, there are at any given moment 12 models that you could find and look at. And if you want to do an ensemble, well, you have to do it sort of mentally. Let's see, the GFS said this and NAM said this, and what the heck did the SRAF say? And oh yeah, I can't forget, what's the UK, the United Kingdom high resolution models say? And they all say they're the best. Although the ECMWF, the European weather forecast model, European Common Market, WF weather forecast, something like that, is generally regarded as the best. But it's the best in forecasting the dynamics. The solution of those primitive equations is not necessarily the best on getting cloud cover and precipitation and wind right. But sometimes I'll go to the ECMWF when I need a really long range forecast because they do tend to work better.
Well, I think that you're doing the predictions for the solar eclipse groups. And I'm thinking sometimes they have the eclipse, you know, in the water on a boat or something like that. Is it a more difficult thing to do when you're in the water than on land?
It's a yes and no answer because first of all, you don't have to worry about mountains. You don't have to worry about lakes. But you do have to worry about the fact that you don't have a weather station 1.5 kilometers away that's taking measurements for you. You have to rely on the measurements that are extracted from the satellite images. So I'd say no, it's tougher. And when I'm doing forecasting on a ship, say, I'm keeping my options open until I see the satellite pictures. There are places where I can get a satellite picture zoomed in on any point of the globe. Well, maybe not any point. I can't do it with the Chinese and the satellites. I can get pictures, but I can't zoom in on them. They don't have, I mean, there are sites in the States with interactive, you click on them and it'll give you. So I rely a lot on models. In the end, it's satellite images the night before and looking at the sky when sun comes up. So far, I haven't been clouded out on a ship, but it's only a matter of time. I'm going to be on another one in April. We'll see if I still have that.
Over to Scott.
God.
We have a question from online. Let me unmute my microphone. Jim McGregor's asking, to your knowledge, does our local media rely on Environment Canada predictions, or do they refer to other or additional sources?
CBC and probably all of them use commercial providers that use Environment Canada's models. So there are very few weather outfits that run their own models, and they'll be the big ones. AccuWeather, the Weather Network will run their own models, and they probably nest it within the National Weather Service models from the United States. What you're seeing in these sites I'm showing you are the National Weather Service forecast. Thing is, you go to a television station, they don't say, well, one model says it's going to be cloudy and the next one says we're going to miss it. They'll give you one or the other. But I know that John Sauter has to agonize over knowing that one model is saying something, but he gets a package from the company that the CBC is contracting with, and that has all of the graphics. And in those graphics are where they think the cloud is going to be. And he can modify that, but it's a lot of work for him. So more or less, so they're kind of using the government models, but they're using it after it's been tailored by somebody else. By doing it this way, you get to see the raw data in a sense, and you can make up your own mind, and you can see where the people on TV and radio should be more uncertain than the sort of, this is what's going to happen attitude. John's good because he does give you that, we're watching it. It looks like it's going to hit us, but we're pretty close to the edge, could miss. Environment Canada doesn't do that. They say, yes, you're going to get it, or no, you're not. They're not allowed to express the uncertainty. They have to say, you're going to get it, or maybe 40% chance of snow and things like that.
Question. Like you were showing the map that you liked, it was animated map with the upper level water vapor. I'm just wondering, where is that data from? Is that radar or satellite?
Oh no, it comes from the GOES satellites, the geostationary operational environmental satellite, standard ones that are in geostationary orbit looking down at us. There's an east-west, and east GOES and a west GOES, so sometimes you're looking out in one or the other. And in the case of the College of DuPage, they merge the two of them together, and then they rectify it so you don't see the curve of the earth anymore. So it looks like a flat image. So it's basically invisible to you that they're looking at two satellites. But the Western states will have the Pacific GOES, and the Eastern ones will have the Caribbean GOES, and the dividing line between them is pretty close to right through Winnipeg.
So there are several GOES satellites? Are there several GOES satellites?
Oh yeah, there's a whole passel of them up there. There's two new ones that are in storage waiting till they're needed. There's a bunch of old ones. What we're on GOES 15 or 16 now. When the sensors fail on these old satellites, only one of them will go. The infrared sensor might go. So they still use it for communications. They still use it for measuring solar activity. They still measure it for all the other things they do. Sounding data, which is measurements of the parameters through the atmosphere. They're pretty reluctant to turn a satellite off, although they will do it eventually when they have enough new ones to cover everything off.
What does GOES stand for?
Geostationary operational environmental satellite or something like that. Too much to say all at once. And then there are polar orbiting satellites too that come over every day.
Another question from online is Ed Johnson asks, what does 40% chance of snow mean? Is it that 40% of the time it will snow given those conditions?
That's what Environment Canada would have you believe. But in fact, if you analyze it mathematically, it means that 40% of the region they're forecasting for will get snow. So there's a difference between, it's precision and accuracy type of thing. And the other thing is that 40% of the time you say 40% chance of snow, it should snow. And the other 60%, well, as it turns out, I can't remember what the numbers are, but they're way off. It's either 10% or 60%. So they're way off. The problem is one of area. You can get snowfall pretty accurately. because it's a big area thing. Thunderstorms are a completely different thing, much tougher to do. And a lot of times you get a 30% or 60% chance of rain on a thunderstorm day, then you'll watch them go by over the south part of the north part of the city and miss you completely. And that's where you might say, well, that 40% or 60% could be accurate. And if you wanted to map out, one of the things is we measure precipitation so inaccurately, especially snow, that we probably couldn't answer your question or that question about whether 40%. But theoretically, it means that 40% of the region will get precipitation, but the way it's portrayed is that 60% of the chance you won't get anything. Nobody in the region gets anything, and 40% everybody gets something. It doesn't work that way. Okay.
Way up the top there, Danielle.
So, very early on, we were talking about grids, and it looked like there was high resolution at the bottom, and then again at the top of the atmosphere. Why do you have high resolution at the top of the atmosphere?
Well, part of it is for ozone forecasting. Part of it is this boundary condition thing that I discussed for in the horizontal thing. There's no zero in the atmosphere, at least in the levels that we're dealing with. So they approach it kind of cautiously. There's also a lot of things that happen at the upper atmosphere that are pretty important, not so much for what happens at the surface, but what happens in the higher levels and down toward the mid levels of the atmosphere. We're beginning to see that even a lot more. But primarily the model data sheets will tell you that it's primarily for the forecasting of gas species in the upper atmosphere. Probably a simpler calculation in some respects because you're not really dealing with a lot of humidity and adiabatic changes and things like that at that level.
I have to ask the artificial intelligence question. Do you know, are they using AI to improve weather forecasting? And I guess what I'm thinking of is, if you have a model, you have your fluid dynamics and thermodynamic model that's predicting this, and then you have an error that you know from once you get to that point in time, you can actually compare it. You have an error, and you could actually use that to train an AI model to actually make a forecast there. You know, that's that.
Well, you saw those equations. Some of them have to be solved iteratively, means they don't have a solution, a direct solution. My experience with AI, and we experimented with early parts of it in the 1990s in the weather office, is you have a data set you train it on. Okay. And then you have a data set that you test it on. And you would train it, and you'd get, if you do it enough, you can get 98% time you're correct. And then you take a data set it's never seen, and it's 84% correct, which is still pretty good. And we're talking temperature here. And then you go out into the real world and you give it today's data, and the accuracy suddenly drops to 52%. Now,
which is guessing, basically.
Well, it's at the stage where the forecasters won't use it,
right? Because
the forecast they get. Now, one thing I didn't show you, let's see where I can go here. This will be hot weather. And all these choices, oops, that's not what I want to do. All these choices that you have here at the bottom is this mysterious thing called 3.5 day scribe. Now, scribe is the AI program that feeds the forecasters the forecast. In other words, this has been post-processed from the models. And so you get the scribe forecast on your desk when you begin to write the forecast in the weather office. And you are allowed to change the first 24 to 36 hours. Beyond that, you can't touch it. Or you can touch it only with an explanation left that you can convince the supervisor. if you have critical numbers, the scribe forecast might be your best choice because that's the one that's going to be closest to the weather forecast you get. And it's not perfect because the forecasters do modify these things quite a bit when they look at the satellite images. And it's a limited number of things. This Showalter thing is a stability index and so on and so forth. So if you have critical need of precipitation and temperature, you might want to look at the scribe as kind of the last best guess. And then just to make life complicated for you, you can have a scribe based on the RDPS or the GDPS, and we won't go into that. And then they also have an extended scribe here that goes out 4 to 6 days. So that might be the one, if you just got casual forecasting, you might want to just look at those and go with it. I think statistically, they're probably the best ones. Are we done?
It's just a curiosity. I assume the accuracy of weather forecast depends on the number of water, the amount of water. So is there a place on the planet where weather forecasts are the most robust, the best?
Sure, in Canada. You'll never get a better temperature forecast than in Vancouver. Because the highest temperature they ever get in Vancouver is 27 and the lowest they ever get is -5. And so you're always got a narrow range. And if you want to go to the Caribbean, it gets a lot better. And you go to Brazil, rains at 4 o'clock every afternoon. It stops at 6:30 in the sun. So yeah, it depends on the climatology. And we have a tough one here because we have a +40 at the top end of our temperatures and a -40 at the bottom. We have an 80-degree spread in temperatures that over the course of a year. So yeah, it's strictly climatology as to where the best ones are.
All right, well, thank you very much, Dave.
Oh, you're quite welcome. Can we stop the share?
Sure, that's fine. Well, thank you very much, everybody. For those that are interested, over at Boston Pizza, there's a get together afterwards. And for all those that joined us online tonight, thank you very much for coming. And we'll see you all in the next year as it goes. Have a good evening.
Thank you. Everything worked.
Yeah, everything worked. It went well. Thanks, Jake.
Ed, are we leaving the Zoom meeting open for people to socialize on it or not? Oh, okay. Okay.
Yeah, Sylvia still has t-shirts, still some magazines up front if you're interested. We'll get together over coffee.
Hey, how are you?
Good, so?
Good, good.
Oh, super. Thanks.
No problem. Before I forget, because otherwise I'm just gonna forget. I'm just
Cold the other night, eh?
oh my gosh. My focuser. Oh yeah. It would still go out, but it wouldn't go in. It just didn't have the jam to pull it back up with the weight. I have a filter wheel on there, and it was just too much stuff.
I had my small scope out, and I put the focuser on that, and that was kind of a bad mistake.
Oh yeah.
I think next time I'm going to wrap a dew heater around it or something like that.
Well, that's a great idea.
So let's see how that works.
That's a great idea.
Yeah.
Oh yeah.
I was looking at dew heaters today on Ontario telescope.
Okay.
And probably put an order in on Monday. But
Well, we're just about to post that we're getting RAC members will get a 5% discount through Canada Telescopes as well as David Astro.
Canada
Telescopes. Yeah. So both of those places. Actually, Kevin Galka. I don't see him here, but do you know Kevin?
not really. No.
Okay. I will, in the next day or so, get his email, and basically you just email him, he gives you the discount code, because he works for them as a tech support guy remotely. And so we get
I met him at the Star Party.
Yeah,
I think he was out there.
yeah. So, yeah, he secured for us a 5% discount on everything through Canada Telescopes. So, I mean, 5% is the GST basically, but, yeah, the dew heater is a great idea, because that was just one of those Velcro strips. And yeah. I did go over and give everything a blast with the hair dryer beforehand, but obviously it didn't last.
Yeah,
so just got
that would probably create some condensation, then freeze up maybe.
Yeah, you know, that's probably true. I just did the focuser area and stuff, but still, yeah, no, that's a good point. Wow. Well, it was a nice night, and I was talking to Stan. He and I, neither of us can remember seeing a planet occultation at all. I mean, I know they've happened, but maybe not where we are, or maybe it was cloudy or whatever, but I don't remember seeing a bright planet. Or yeah, exactly. So that was pretty spectacular.
Yeah, well,